This call
Good
is
day,
now being recorded.
good day, everybody. Today's seminar will be presented by Sumit Mukherjee. Currently, he is a postdoc at Korea Research Institute of Standard and Science, Greece, at the Republic of Korea. He did his PhD with Dr. Olav Pran from NIT Patna. Today, he will be talking about a little bit of contextuality and how we can quantify the contextual action and we can use it as a measure of contextuality. So, Sumit, over to you.
Okay. Thank you, Shorodipda, for the introduction. So, as you said, so I will be talking about some measure of contextuality today. Maybe every one of us at least know a little bit about contextuality and at least heard about this term in quantum foundations and information theory. So, so I will before starting the discussion of how to quantify contextuality, I want to very briefly just tell what contextuality is, as brief as possible. So, and also one caution is that when I talk about contextuality today in the whole talk, I will only be considering the former form of contextuality, which is sometimes called Kochen-Specker kind of contextuality, and is based on the measurements, and not the modern kind of Speckens or a generalized kind of contextuality. So always my talk will be circled around this former notion of contextuality. Okay, so just to briefly mention what contextuality is, I will recall the discussion that we had last week by Anando, where he has introduced ontological models. But I will not go into the ontological model. Just I will recall that and will define what contextuality is. So just consider this table. One side there is quantum theory, and another side there is ontological models. So from the last week's discussion, you know that quantum theoretical tools are this row, which are quantum states, and the measurements, and the corresponding things in the ontological model is some distribution over some hidden variable lambda due to this state row. And for measurement, the corresponding thing for the outcome of a measurement is called the response function. So it is written like this. So that means a probability that I get an outcome k when I have done a measurement m and when the prepared state is represented by lambda. So this is that probability. So because we will be discussing on measurement contextuality kind of thing, so this is most important thing in our discussion. So this response function. So now we know that in this ontological model or a realist framework or whatever we see in everyday world, there every observable quantity has you can measure it without affecting other observable quantity. So that means if you want to measure one quantity, there is no restriction that other quantity will be like disturbed or something like that. At least fundamentally there is no such restrictions. But in quantum theory, you know that there is some fundamental restrictions by this Heisenberg's uncertainty relation and all. So you do not have simultaneous values of all observables together. So but some observable can have simultaneous values in quantum theory also. So very roughly we say in quantum theoretical prescription, we say if two operators corresponding to observable, let's say A and B, they commute, then these two observables have simultaneous value. That means I can measure these two things without affecting one another. So just consider this one, A and B is commuting, and also consider another, A and C is commuting. Then inside quantum theory, A and B has simultaneous value, A and C has a simultaneous value. Now this A has a corresponding response function in the ontological model.
Sumit, I have
Yeah.
just one question here.
Yes.
So, I mean, what did you just mention? These things that AB is commuting, A is observable, B is another observable, which is commuting. You mentioned
Yes.
this way, right?
Yes.
So, but it is not very. I mean, so you are taking a structure of. You are taking some structure, I mean, some mathematics with it. I mean, some matrix, right, for A and B.
Yes. So in
But
this
it is
case,
nothing to associate with real things. It is just a mathematics. Right?
This is just I am considering the quantum theoretical tool, you can say.
Okay,
I mean,
some tools, some mathematics
inside the quantum theoretical tool. So observables are represented by matrices in quantum theory, and if two such Hermitian matrices they commute, we say that this observable corresponding to these matrices has simultaneous values, right? So I'm just considering quantum theory for this case, not ontological models. I mean, this is one rough way. Maybe you have in general way like joint measurability and those kind of things. But for now, just consider this very rough thing. Like if two observable commutes, two operator commutes, they have simultaneous values. So then the conclusion is that then A and B can be measured simultaneously, and A and C can also be measured simultaneously. And as I said that there will be a corresponding response function. Let's consider that this is some K A lambda, and let's say if this, so I am defining this by C1 and this by C2. I will say that these are context. Like once A is measured with B and another time A is measured with C. So A is appearing in two different contexts. So I will write this like this: C1 and another response function in the context C2. I measured the same observable, but at different context. So the assumptions of contextuality essentially is this, that C K A lambda equals to C2 K A lambda. Okay, that means in the corresponding ontological model of quantum theory, the response functions do not depend on the context. It only depends on A and lambda. So if this is true for all K, then I mean there is no measurement outcome that can distinguish these two realist description of the measurements. Then we say this is a non-contextual description of the response function. So this is one assumption. And if I add another assumption that these response functions A lambda, it takes value 0 and 1, that means this response function are deterministic, then this whole thing is actually the assumption of Kochen-Specker non-contextuality. Right? That means this non-contextuality plus determinism, and determinism for the projectors. So this is to be precise. Like in the Kochen-Specker contextuality, the determinism at the level of projectors. So all the response function corresponding to the projectors has 0 or 1 values. So these two assumptions sum up to the Kochen-Specker non-contextuality assumption. So in the conventional contextuality discussion, what we basically do in maybe in some information processing task or different foundational issues, what we basically do is that we take this assumption to be true, this kind of assumption to be true, and then we formulate some function of probabilities, and then we give a bound, maybe this or this, to this function of probabilities by assuming that Kochen-Specker kind of non-contextuality assumption. And if this is violated by quantum theory, we say that the ontological model corresponding to quantum theory has a contextual description. This is the precise way of saying that. And now, if this FP, what I have written here, if it represents some kind of figure of merit in some information processing task or any kind of task, then we say, okay, then my quantum advantage is actually contextual advantage because I am getting a more value by using quantum theoretical tool, which cannot be explained by some non-contextual ontological model. So we say that in this information processing task, contextuality is actually providing the advantage. So there are many such things like inequalities. This kind of inequalities, one is KCBS, another is like this Pires-Marmin or Cavallo kind of inequalities. But let's say there is one inequality, F1P less than equals to beta. Now, the question is that, let's assume that quantum theory is violating it. And for quantum theory, I calculated FQP is equals to some beta Q, right? And which is greater than beta. Then this is the amount of violation of this inequality. Now the question is that, can I say that more the violation of this inequality, more is the contextuality in the scenario? The answer is no. I cannot just claim that. I have to prove many things before that if I want to claim that. I mean, just consider like you have a KCBS inequality and you have a violation of KCBS inequality, and you are saying that more the violation of KCBS inequality in my scenario, more will be the contextuality in my scenario. So
Sumit, I have a question. What do you mean by more contextuality?
Yeah, that I will be defining. Maybe there are many ways to define contextuality, but if I don't define the measure of contextuality, there is no meaning of saying how much amount of contextuality, right?
Yes, I mean, intuitively, what you want to see by the meaning of more contextuality in that way, because you are saying that the amount of inequality violation doesn't correspond to that notion, but intuitively we can think it like that. So that means you have something in your mind about what do you mean by more contextual, less contextual.
So that is what is the motivation of this today's discussion.
Okay.
So first, at the first place, I have to define what.
Sumit, before that, I have some questions regarding this P. Okay.
Okay.
So how this P looks like? So P is a probability, and this probability is, you are saying this probability. Can you write it for me? It is some behavior. P.
Any probability behavior, like
any probability.
Say I have two measurements, A and B. So this kind of probabilities.
Yeah, but I want to understand more simply. For example, this P is equal to, so this P is a probability when you are measuring A. So that means this P is equal to K given A. Can you write it for me? P is equal to K given A.
K given A? This?
Yes. And so this is the observable probability, right? This P K given A?
Yes.
So actually, this is actually summation of, you write, this is summation of, this probability comes summation of lambda.
Yeah, this is just, you are saying
response
this,
function.
Right?
Here is not probability, it is response function.
Yeah,
right?
Here
it would be response functions, right?
Yes. Maybe I can write it like this.
Yes.
You are saying this,
with
right?
Some, with some lambda probability, mu lambda.
With some lambda probabilities. Yes.
So that is your actually ontological response functions, and this K given A is your actually observed statistics.
Observed statistics, yes.
Statistics. Okay, so now you have some set of this K given A observed statistics. On that you are defining some function f, which is some beta Ka, right? So you can write this f fp is equal to sum over beta k, so kai, because I require different a, right? Because
Yes,
for a
yes.
single a, it would not be possible, right?
It is not possible, yes.
So now my question is, what is the easiest, or what is the so far very simple or very elegant? I mean, so is there anything like I can choose only two different a?
Oh, you
And
are saying
then come
what
up-
is the most
what is the
simple
minimal?
case to reveal
Simple case.
contextuality?
Yes. Yes.
So for this Kochen-Specker kind of contextuality, this Cabellow's 18 vector proof is there. So there you need at least 18 such vectors, and
Those are k.
yeah,
Those are k, right?
those corresponds to k. So maybe 1k appears in two contexts, in two measurements.
Okay.
So something like
Okay.
this. So there are more simpler proof like 13 vectors proof by U and O and all. So people are trying to make it simpler and simpler. So first proof was by 17 vectors by Kochen-Specker.
Okay.
So
Okay. Okay.
so this
So
this
the
research is going
simplest
on.
one. Okay. Okay. Got it. Thank you. Because we know that Bell inequality is two input, two output, those things.
Yes,
right?
yes.
So yeah.
So
Okay.
I will
Okay,
just
thank you.
come in Bell inequality for an example. Yeah.
Nice. Thank you.
So okay. So
Okay,
so
Sumit,
this is
another
the
thing.
Huh.
Another thing, let's say in your observed land, you will get a probability vector, which is a set of all probability distribution, right? For
Right,
different
right.
measurement, different outcomes, something like that.
Right.
And from your ontological model, you can try to predict that operational probability, right? So you will get another probability vector, which is directly coming from ontological model.
Yes.
So now
But
you
that
have two. And now let's say you have two probability vector. One is from ontological model and another
yes.
what you observe in your lab.
Right. Right.
Now we can define a distance measure between these two probability vectors. And
The
then,
observed and ontological?
yes, you have observed probability vector and you have ontological probability vector.
But
Now
how
one
can you like define a distance between ontological
because they are
vector
two
and
vectors. No. From ontological model,
but
ultimately you will get
but that should be in the same
Space.
dimension, right?
Okay.
same dimension. Let's say
Exactly.
But
example,
how can but there is no guarantee that the dimension of the ontological space vector is equal to the dimension of the observed statistics state vector.
No. I understand. Let's say in your ontological model, you have this response function and mu, right? From there,
Yeah.
by summing over all lambda, you will ultimately get a probability vector in your operational lab. Right? The origin of that probability vector is the ontic node. That is the origin.
Right.
And some probability vector that you can observe in your lab. That origin I don't know. Maybe it is coming from ontological model. Maybe it is coming from quantum mechanics. I am not bothered about it. Right? Now these two probability vector are in same dimension because number of events are already you have defined before your experiment, right? That I want to press two buttons, I want to see two outcomes, this kind of thing.
Yes.
So now one can define a distance between these two probability vector and try to minimize it over all possible ontological. And whenever it will be zero, we will say, okay, my observed probability behavior is actually, my observed probability vector is actually equal to some kind of probability vector which has an origin in ontological.
But how can you claim that?
No,
I think Suradeva, what is sorry, Nirbanda, please.
Shoradev, I had one question that even if they have the same dimension, that does not mean that they are coming from the same spatial structure.
Yes, that is true.
Come to the same space. They can have same dimensions.
Yes.
So over there, if they are coming from different spaces, that means different algebraic structures, you cannot define a distance between them.
Yes.
Even though the dimension can be same. So
because they are completely different spaces, so you cannot compare them.
But here I want to add with Suradipta's word. I mean, so suppose, how Suradipta was saying, if I'm correct, Suradipta, please correct me. So suppose you are defining these functions over this P, K given A, right? So K has multiple numbers, A has multiple things, A1, A2, right? So we can always find a matrix like for phi K given A, right? And then can you write it for me?
Yeah. Say.
So
Neil,
you in the
Neil,
Nirmal.
what you are actually trying to say is that you can take a map from one space to another space. That mapping is possible. For example, what I'm telling you, that if you take for example the 2x2 matrices, then you can generate them by 4 2x2 basis matrices. Okay, so the
Exactly.
dimension there is 4.
Yes.
Okay, now
Yes.
you can also take R4. R4 also has a dimension 4. Okay,
Yes.
so R4 means I'm talking about a 4x1 vector. So you have a 4x1 vector, and over there you have 2x2 matrices. Both have the dimension 4, but you cannot define
Right.
a difference between a vector and a matrix.
No. So that's why
Yeah,
what I'll do.
understood. Okay.
Yeah,
Okay.
but
That's
I
why
Let me.
think this, what
Suradipta.
Shododipta is concerned about, that will come in this talk, because I will also represent this ontological model by vectors and operational statistics by
Good.
vectors. So
Okay,
maybe
that
that
means-
will be clear.
That means there will be some kind of a mapping. If you use a some kind
Exactly.
yes,
Right,
for
right.
example, if there are two spaces which have the same dimension, then you can always bring in some isomorphism.
Exactly.
Okay.
Actually, I think Suradipta is also talking about this
Yes,
isomorphism.
by
This, every this.
yes, by bringing an isomorphism, you can now define a
Yes.
distance if you can bring it to the same space.
So
Yes.
I'm just wanted to just finally conclude these things that, okay, I have some behavior pk given m a. I write them in a matrix n cross 1. Okay,
Right.
and then I'll find a polytope for this n cross 1, and maybe for all those non-contextual model, I can actually find a polytope. Okay.
Yes.
Now, if I get a point which is outside of that polytope, okay, so that means it is contextual point.
Right.
And now I think what he's saying that, okay, let's find the distance of that outside point with the whole set, the minimum
Right.
distance.
Right with that. I
That is
just
the
wanted
contextual
to
definition.
tell that. Yes. Exactly. So in that way, one can construct the non-contextual polytope, and whenever you will see a observed behavior in your lab, you will just try to define the distance of your observed point and all the vertices of the polytope. And in that way, one can see that how much, where the point is. First, one can try to see whether the point is outside the polytope, on the polytope, or inside the polytope. And if it is outside, then how much outside it is. And from there, maybe can we say that this is my this should be my quantity of interest, that amount of contextuality, how far it is from the outside the polytope.
So I think you will. Sorry.
Just one thing that I just wanted to clarify. So what actually you are doing over here is that you are taking the behaviors which are forming a non-contextual set. Now you have a point. You have a behavior which is outside that non-contextual set, and now you are actually finding out the nearest non-contextual set to the context.
Exactly.
That will form a measure of the contextuality.
Exactly.
Yeah, that was my intuition that whether
I think
Sumit will ultimately go there.
Sumit would also go there. Okay, let's see.
Yes. Kind of that, actually. Yes.
Okay. Please proceed.
Okay. So I was just telling about the quantification of contextuality when all this argument comes. So another problem is that this, if you know that this Kochen-Specker kind of contextuality is formulated in a theory-dependent manner. There is no definition of Kochen-Specker non-contextuality without assuming quantum theory, because at the end of the day, you are assuming deterministic response function corresponding to the projectors, and projectors are a tool of quantum theory, right? So there is no definition of Kochen-Specker kind of non-contextuality without assuming quantum theory. So can we formulate a contextuality assumption, non-contextuality assumption without assuming any theory? So that is another concern. So in today's discussion, we will do both of them. One is quantifying them, and another thing is defining the contextuality itself without assuming any theory. So, okay, how to do that? So, just
defining non-contextuality without
defining
assuming any theory.
Yeah, without assuming any theory. So, I'll start differently then, from a different angle. So, now just concentrate on the definition that I am giving. So, a measurement scenario. So, I will say I have a triple this, say this X, M, and O. This is called a measurement scenario. So, what is this? So, X is the set of measurement that you are using in your lab. M is what? M is the subsets from this set X, those can be performed jointly. Okay. Okay. And O is the set of outcomes. So this is my scenario. So if I give an example how it works, let's say you have the famous CHSH kind of scenario, 2 party and 2 output and these things. So for that thing, what will be my X? X will be A1, A2, B1 and B2, right? For the CSHH. What will be my M? So I defined M that subsets of X that can be performed jointly. So in a CHSH kind of scenario, what can be performed jointly? A1 can be performed with B1. A1 can be performed with B2. A2 can be performed with B1. And A2 can be performed with B2. Right? So this forms the set of M. And O is, I'm just assuming this is 0 and 1. Okay. So this is for the CHSH case. I'm just giving an example what a measurement scenario looks like. So this is the first definition. The second definition is empirical model. What is an empirical model? So empirical model is the behaviors, what you are talking about some times ago. So if I have such probabilities in the CHSH scenario, A, B, and given AV, I can make a table, right? Something like this, A, B. So say A1, B1, A1, B2, A2, B1, and A2, B2. And those are outcomes. Right? So there will be some values here and here and here. Those are the probabilities. You performed experiments with A and B with some state, and you can gather this data to generate this table always in the lab, right? So I will say that this table is the empirical model because it consists of empirical data. Okay, so these are my two definitions. One is measurement scenario, and given a measurement scenario, there will be an empirical model. So based on how your nature or how your experiment works, based on which theory, this table will be different. This table will be different. Like if you take quantum theory and the observable corresponding to the quantum theory, you will get a specific data in these points. If you take your PR box, you will get different data, right? So based on your theory, this data in the empirical model will be defined. So my question is that given an empirical model, this is everything. You are observing it in experiment. That means this is everything what you have. Now you have to explain this data with your theory. So now I am giving you one such empirical model that I observed in my experiment, and I will ask you, do you have a non-contextual model that can describe this data table? So that is my concern first. So to do that, let me first define this notation. So I will be following the notation of this paper by Abramowski, which is in the reference, because when you read the paper, you will be convenient with this notation. So I also found that this notation is the optimized notation. I mean, like, do not have more jargons or kind of things. Okay, so I will always write a probability for a state, like for a context, by EC. Okay, EC means, as I said, that C is a context. So okay, I have not defined it, right? So every one here is one C. Say this is C2. So in here also I can define this is C1, this is C2, this is C3, and this is C4. That means the measurement that can be performed jointly, those constitute one context. That means there is a joint probability because they can be performed jointly, so there will be a joint probability. So that joint probability for a context C will be defined by EC. And when we'll write something like this, say S, just assume that S is the outcomes of this C. Okay. So like for this scenario, maybe you can say that if I write, say, E C1 0 0, this means that this one A1 B1 0 0. Okay, something like this. Just assume this. So I will use these notations while defining everything. Okay. So how to define non-contextuality in this scenario? So you are observing that I haven't used any theory while giving these two definitions. So measurement scenario, which you always have in your experiment, and this empirical model you get from your experiment. So I have not talked about any theory. Okay. So how to define non-contextuality by considering these two definitions? So there is, I can write, let's say I have two contexts, C1 and C2. You can assume this context are these things. So I have, let's say, two contexts, C1 and C2, and I take okay. So I define this. What is this? That means the probability that something has in context C1 will have the same probability if I pick the same thing from different context, from C2. So for the above example, what is that? So I assume A1 B1 and A1 B2. So this is my context C1, this is my context C2, right? So what is this overlap then? C1, this C2, this is just this A1, right? So that means what? That I am picking A1 both the times from the, like once from the C1 context and another time from C2 context. I'm taking from the overlap region, which is A1. So that should give the same probabilities. This is, in the CHS scenario, you can realize this is just the setting independence kind of assumption, right? Because the C1's probability does not depend what B1 or B2 you have performed in other side. So in the right. CHSH kind of scenario, this is basically the setting independence assumption. No?
Yes.
But that is a particular case. You don't have to assume any theory or quantum theory or spatial separation, anything. For any theory, I can define this, right?
Right. Okay. I mean, A1, B1, and A1, B2 can be a sequential scenario, can be anything, can be
it can be anything, any arbitrary scenario.
Any way I can think of it. But yes. The A1, B1 should be jointly measurable, and A1, B1, B2 should be jointly. It should come from the X. M.
Only this. Yes.
M.
Yes.
Yeah.
Yes. So now my question is that let's say I have given you a empirical model, that means a data table, and that data table respect this assumption. Assumption, not this relation. Respect this relation. So my question is that if a data table respect this relation, can that data table can be explained by a hidden variable model or some kind of ontological model, which I will define, which is something like this. So let's say D is a distribution on OX. OX is what? The outcome of all the measurements. This constitutes that set. OX. X was the measurement, and OX is the outcomes of all the measurements inside the set X. Okay. So can I define a distribution D over, like a probability distribution D, over the set of all outcomes, such that when I just condition on C, it will return back my EC? Is it possible? This is the question. So
Sumit,
is it clear?
Sumit, I
No.
got little bit
Can you
confused
please-
in your.
Sumit, can you please repeat this?
Yes. Let's say this D, this is the distribution that you understood, right? This is the distribution over all the outcomes of all the measurements in X. Okay. So that is
Yes.
clear, right? D is clear.
Yeah.
So let's say I have given you a D that gives distribution over all the outcome of all the measurements. Now, given that D, if I just say that picks the context C, can it return back my EC that I should get from this probability table? If for all C I can do this, then I can say, okay, this empirical model has a hidden variable description, right?
Okay, you have actually told many things here. So the D is distribution on all outcomes, all possible
outcomes
outcomes.
of all the measurements.
So that means here, what should be the possibility? 0, 0, 0, 1, 1, 0, 1. This should
1,
be
1.
my 4 possibility, right?
Yes.
Not only that, the possibility should be like that. 0, 0 come from 1, 1 measurement. 0, 0 come from 1, 2 measurement.
Right.
So then
So 16.
I
There will
have
be 16.
16 events of
Yes.
these outcome pairs, right?
Yes.
Now your D is some kind of distribution on these 16 events. So can I say
Yes.
that this D is basically nothing but probability of outcome for AI, outcome for BJ. Your D is something like this, right? The set of this probability.
Yes.
Now you want to say that if this kind of distribution exists, and if I take a marginal out of it, and if I set my context, let's say it is A1, B1 or A1, B2, if I fix my context, then from that 16-dimensional thing, I will get a 4-dimensional probability distribution.
Right.
And now if it same as EC, which is again the probability distribution for the context A1, B1, let's say.
Yes.
Then you are saying that a non-contextual ontic model will exist.
That means what? You have a hidden thing which is defined by this D. From there, just specifying the context, you can pick the right probability distribution from the table. You can reproduce.
Okay,
right?
so then how it is different from the Fine's theory that existence of joint probability implies local ontic model, right? That is although in CSSH context, but the mathematical argument will be same if you just
Yes,
this
is actually the same, because you have one joint probability over like P.
I mean, this is the really big joint probability without any condition.
B2, A1, A2, B1, B2. This is this distribution, right? This one.
Yes.
And
in form of IJ, so you will get 16 elements in there.
If by some marginalization, if I can reproduce some A1, B1 for each context, A1, B1, it is just one probability. But if I can do it for all such context, then I say that there exists a hidden variable model for this, right?
Yes.
That is the what you are saying for Fine's theorem also it is true. So
Yes.
from there only these concepts comes. That means you have a global distribution over something. From there, you can reproduce the probabilities of every context. There is no contradiction. If you find one contradiction that, okay, from this probability I reproduce this one, but I cannot reproduce this one, A1, B2 maybe. I cannot do this. Then there is a contradiction. Then there does not exist such a model. But if you can do it for all the C, yeah.
So can I write this global probability? It is something like, it is not conditional. It should be not conditional probability. It's like probability of A, B, capital A, capital B, right?
Yes, that is this one, right? This one I have written.
Yeah, but you put the condition on capital A1, capital A, capital B.
No, these are outcomes. These are outcomes. These are measurements.
Okay.
Yeah.
Okay.
So I just written this notation. So A1, B1 is, let's say, 0, 1.
I understand. So there are 16 events.
Yeah, there are actually 16 events. So if I give you in your language, then these 16 events can constitute a vector in 16-dimensional real vector space.
Right.
Yeah.
Sumit,
So I'll just come to that. Yeah. Yeah.
With this language, with this probability vector language, how you have mentioned, can you define the above condition E C1 given C1 intersection C2? I mean, just to understand that above condition.
You just take the sum over the other events which you don't
B1,
want.
B2.
Yes. You just
So I can
take
just
the
write.
marginal one and
So
okay.
E
That
say,
Sumit, wait. I
E.
think Dilwanda is trying to ask one question.
Yes.
So it's
Som.
me, Som. So I just
Som.
wanted to say something for the Meer's question. So what Meer said that in the language of Shauradip, the condition, the restriction condition, E of C1 restricted to C1 intersection C2, that's basically a kind of no signaling. You can just formulate it and it will be same as the no signaling condition.
No, it doesn't have
particular
to.
case,
If
if there
you
no
don't have,
signaling.
yes, if you don't have
No,
specified
no,
separated event, then there is no question about nothing, because it is true for each
Yeah.
event.
Yeah, then in that case, it would be some other kind of operational equivalence, I would say, like for the sequential scenario, there would be like, the mark of condition, kind of arrow of time condition is there. Like, there are other operational equivalents depending on the thing. So that things will come from the restriction map there, like that. EC
Yes, one can.
restricted.
Yeah, that is just another language of the same.
Yes, one
physics.
can interpret in a different principal way depending on your different situation scenarios.
Yes.
Yeah, but everything will be like in terms of those restriction condition. Like whatever condition operationally you can think that
Yes,
would
what I
come
think is
from
Sumit
one
is just about to write.
restriction.
That is the fundamental constraint. And now, depending on the scenario,
yes.
one can name it different terminology.
Yes.
Sumit, please write it in the probability.
Actually, what Mirda was asking, so I have written this one, this restriction. So how to write this actually in probability term? So C given something, that means from the context I just picked U. This means actually, okay. So this will be something like this. So this S, and S is what? S is actually in OC, but those OC that are actually in T. Okay. So this T is in OU. So OU, understand, the U is some measurement. For that measurement, the outcome set is OU. So if T is in OU, then you can write it like this, no? Like you have
Yes.
A1, B. So in the formal language which we know, say A1, B1, let's say. So how we write it? So sorry, this one is, yeah, A1. We write it like this, no? A1, B1. So sum over P1, no? Something like this. So this
Yes.
is, see, this is actually same in this notation.
Okay.
So only the thing is that this whole thing is now given by this notation.
So basically, Sumit, those are some linear constraint, right? On the total joint probability space, the big probability space. The global
Yes.
joint probability space, that is a convex space. Maybe this will be a polytope. So then if you are cutting that polytope by providing some linear constraints. And
Yes.
with that, this will give you a smaller polytope. That we will call non-contextual
Non-contextual probability. Exactly.
polytope. This kind of thing.
Exactly.
Okay.
So if that this exists, then that polytope is a restricted polytope, which is a
Right.
non-contextual polytope. Yes.
Right.
Okay. So now I have given you, let's say I have given you one data table, which is an empirical model, and you cannot find such a distribution, such distribution D that can explain all the single probabilities by marginalizing this big probability. You cannot find such D. It can happen, right?
Mhm.
But you are very optimistic person. So you say, okay, I could not reproduce this data table with such a underlying joint probability distribution. Okay, let me write the whole OX. Let me write the whole OX set. Maybe that consists of many hidden variables, G3 and many hidden variables. Okay, let me write the whole hidden variable set OX. Okay, now can I discover at least one hidden variable from this whole set, so that this hidden variable, when conditions over some C is always greater than 0 for all context? Do you understand? This is very important.
No.
Let's say you I am just repeating this. So let's say I have given you one empirical model, and that you could not find one such big distribution that can reproduce all the probabilities, single probabilities in that model. Then you ask, okay, I failed in doing that, but can I do at least something, like at least some events can I reproduce with this kind of
Okay. So
big
that
probability?
means now your given observed behavior, you want to reproduce some parts of it.
Some parts of it, right?
Okay.
So
Okay.
So any probability means what? So total number of events. So in the denominator, and in the numerator is the number of events occurred for that event, right? So that is the probability. So can I explain the fraction of event? So like the question is like this. So now understand, let's say his target is now to find at least one G. G is a hidden variable in this. As I said, that this constitute all outcomes of all measurements. So this is the big probability set. So big data sets actually. Okay. So at least can I find one G such that for all C this is greater than 0? Do you understand why I am writing this? For all C greater than 0, this G. It can also happen, right? So G C E, for C1 this is greater than 0, but E G C2 this is equals to 0. This is also can happen, right? That means in the C2 context, this G has no ability to explain C2 context.
Okay.
Not even a fraction of events. although it can explain these events in this context, but in this context, this G1 is fail to explain events in C2 context.
So G is your events, right?
G is the hidden variables. Maybe you have
Hidden
many
variables.
hidden variables in the set. So some hidden, can I find some hidden variables that can explain the whole statistics without any contradiction? Maybe other hidden variable are failing, but can I select at least some hidden variable that can consistently explain that table, at least a fraction of events?
So then I would say that is hidden with ontological model. It is possible, right?
Hidden
If
variable
one of
means
the
ontic
one
variable,
of
right?
the
First one.
Yes.
Okay.
Ontic variables.
I mean, I'm saying that is the main aim, right? So you already told us that, okay, if some behavior cannot be explained by some ontological way, how you...
No,
then,
but see this probability. This is greater than 0. I haven't said that G given C1 is EC. I haven't said that. I have to reproduce EC, right? EC is my probability table. I'm only saying I am reproducing a fraction of event, only greater than 0, not reproducing EC exactly. I have to reproduce EC. No.
Okay, to reproduce EC, you have to satisfy two things: positivity and the completeness, sum over identity, right?
Completeness, yes.
So now here you are only considering that let's forget about the completeness. We will just take the positivity. That my hidden variable only can explain the positivity. So it will be not EC, but we will know something about it.
So this is some EC, let's say. Okay.
Right.
So EC some S1, EC S2. So this is C1 context, right? C1 context. EC1 S3 and so on. Okay. So my goal is to reproduce. I have given you this OX. OX contains this G1, G2, and so on.
why this is S1, S2, S3? Because all our outputs are A1, B1, right?
Yes.
So your S is equal to A1, B1.
S equals to A1, B1. Yes. No, 0, 0, 0.
0, 0, 0, 0. He took the outcome as 0, 1 and things as A1, B1, A2, B2. Right?
Yes.
Okay.
So it is basically EC1, 0, 0, EC1, 0, 1, this kind of thing.
So my goal is to do this thing. G1 for some C to reproduce these thing, right?
Right.
All the EC1, S1, EC1, S2, and all these things, and for all context, right?
Right. ECI SJ.
That means
that's your goal.
EC. Yes, I have to reproduce EC, but let's say I cannot do that. That I have said previously that I am unable to do that. I have given a very bad empirical model that cannot be reproduced by this kind of large distribution. But can I?
Sumit, I just wanted to. So I'm getting a little bit confused here. So for example, your context, when you're saying your context is different, that means your output is always constant. No, sorry. Your context is different.
Output is same. Settings is different.
Output is same. Output is same. Setting is different. That these 0, 0, 0, 1, 1, 0, 1, 1. These are the measurement, different measurement choice.
Outcome.
So these are the settings,
no,
right?
That is out.
0, 0 outcome. You can observe
Event,
0, 0 event from A1, B1, from A1, B2, from A2, B1, from A2, B2.
So this now above say whatever you have written is 0, 0, 0, 1, 1, 0, 1, 1. These are the outputs.
Yes.
Exactly.
Can you give me 1 minute? I have written it previously also. I'm just trying to explain.
Can you go to the?
So this is actually, you assume A1, B1. Okay. This is exactly this. So this is your S now.
No, just 1 minute. So your capital AB, is it your measurement choice or I mean,
yes, measurement
because
choice.
earlier measurement choice. And what is the small A1 B1? This is also your measurement choice?
No, no, these I have actually written that this is in general. This is AB's
Mm.
measurements, A and B
Maybe
for Alice and Bob.
AB
maybe.
is the measurement operator, right? Observable, you can say. A1 is the choice. In
Yeah,
that way.
A1 is the choice. A1, B1 is the choice.
Okay, I got it. I think yes.
Maybe actually, yeah, it's little bit. What is it? You should.
Because
Sumit, you should write
actually,
it capital A1,
can-
capital B1. What Mir is
Yeah, that will
confused.
be convenient, no?
Yes,
Capital
yes.
A1, capital
Just
B1.
stick with it. Capital AI, capital BJ is your measurement, and maybe
Yes,
small
yes.
AB is your outcome. So because it's
Yes,
more
yes, yes.
usual way of writing.
Maybe Mirza will be more satisfied with this notation, this one, right? A1,
Yeah,
B1.
yeah.
actually, in the very beginning, you mentioned this capital AB is your measurement.
Exactly.
And-
Exactly.
Oh, okay. Maybe I
Yeah,
have
so that's
forgot
why I got confused.
while saying. While
Yeah, you just
progress,
clear
maybe
the
I have
notation
forgot.
first. Yeah. Just
Yeah, yeah.
take the notation same.
And
Okay, so now on, every time I will use this notation. A small A1, B1 will be my measurement choice. Okay.
Sumit, also I have a proposal since we are almost in a ending time, and I know you have a lot of things to talk about. Can we extend this meeting for next week if you are available? Then
Next week, actually, next week I have some work, so I.
maybe in different time, maybe or we can shift it one day
Yeah.
around it, because I know what the point you want to reach. It is little bit far from
Actually,
there, right?
I am seeing that it is far from, not far, but just can you give me 10 minutes? Then I can at least introduce what contextual fraction is. I am
Yes,
almost
obviously.
there.
Yes, please.
Sumit, that is perfectly fine, but this is very interesting topics what you are saying.
Yes, that's why we are so much
I mean,
engaged in
Maybe
this.
I cannot
we
reach
are
the
flexible
resource
with the
theory.
date.
Huh?
Yeah, we are flexible with dates. If you are busy in the next
With
week,
date and time,
just
so
you can take
anytime
it.
next
Yeah.
week.
Okay, I can, the second installment I can give another day.
Right.
Yes.
So just before you proceed, can you just little bit give me an example what the OX set looks like? Is it looks
O?
like OX, capital OX, this set?
Hmm.
You told that this is the total outcome space. Is it look like 00 from C1 context, 00 from C2 context, 00 from C3 context? Whether this set look like this?
So let's say this is 0, 0, 0, 0. So let's say G 0, 0, 0, 1. Now you understood?
So
So I
that
can.
means, so the first thing, first element represents that I got 00 outcome from 1 context, something like that.
Yes.
So can we say the notation should be like this SC1, right? SCI. Then there will be 16 possible combinations.
16 possible combinations. Yes.
Right. Okay.
Yes.
So in your notation, it should 0011, 0012, 0021, and 0022, right?
Right.
Not 40 or 301.
In my notation?
Yes. That
Oh,
event
no.
should be like 00 and 111.
No, it should be 0, 0, 0, 0. So, but for the first two things, this is some
Outcome.
A1, B1, A1, B1, A2, B2 for latter two things, maybe this one.
Okay, later two outcomes. Okay.
Two outcomes, yes.
I mean, when I measure capital A1, capital B1, I got 00.
Yes.
Okay, I understand.
Okay, something
Okay,
like that. I will also give the detailed description of this, how this OX should be. Okay. So now,
now, Sumit,
Yeah.
just in 2 minutes, you tell the notation, I mean, your standardized notation fast. Just in 1 minute. Then I think it would be better.
So I will always
with
say
an example. Yeah.
Settings, capital A1, A2, B1, B2. Outcomes are these 0, 1, these things. And these sometimes I am representing by S, sometimes by T. Okay. So this whole thing is S or T, maybe.
Okay, and if it is, let's say, let's say if it is a outcome of capital A1, sometimes you will also represent like small a1, right? Where small a1 can take value either 0 or 1.
Yes, 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 yes.
No, so you tell complete it.
Okay. So sometimes for the sake of understanding, I am saying that this small a1, small b1, those are the outcomes actually. But whenever I am not writing this probability in terms of probability and writing such kind of notation, I am always using this EC bracket something like this.
Okay.
So is it clear?
Yeah. Okay.
So I'm just then very briefly defining what contextual fraction, because I am almost there. So latter part maybe I will talk later. Okay. So the context. So I said that okay, my goal was to reproduce all the probabilities like this by this G, but I could not do so. I am now finding this G C greater than 0 for all C. I am trying to find it. So let's say I found it. That means I can explain some of the events. No? So what does it mean actually? I have given you one model. Okay. That one model, some fraction I can reproduce by some non-contextual model, but some fraction I could not reproduce. This is some arbitrary no signaling model maybe. Okay. I have given you this model. This model is given. Then the question is, I ask you, can you explain this empirical model by non-contextual assignments? So you said no. Then I ask you, can you explain at least a portion of this data? Then you said, okay, I found some non-contextual model that can explain a portion of data, a fraction of events, but that cannot explain another fraction of events. So then this whole empirical model, so you had a table previously. Now you have a table plus you have another table. So this table can be reproduced by this great probability distribution able, and this not able. Okay.
That 1 minus lambda. It should be 1 minus lambda fraction.
1 minus
It should be something lambda dash. Yeah. So Sumit, can I say, just to understand it properly, that let's say I have a probability distribution which is relation point, like which gives 2 root 2 in CSS scenario. Okay.
Right.
That table I cannot construct a local onto point, that we know. But the question is, can we simulate this table by taking convex mixture of a PR box and some local distribution?
Exactly.
But okay. So if we are considering the whole no signaling polytope, so then any quantum behavior can be written like that in that convex mixture. And from there, one can try to find what is the minimal fraction of local boxes required.
Right.
Oh, okay.
So when you say this, you can also realize that this is not a unique way, right? Because you may give a more contextual thing and less local thing.
Right.
And there are many ways to write it. But what contextual fraction is? The contextual fraction is when you assign the maximum thing here.
Yeah, I mean the maximum locality I can use. The
Maximum
lambda.
locality or non-contextuality you are using.
Non-contextuality in general. Yeah.
And 1 minus lambda e to the power e, say
Some
I will
other.
write it it strongly contextual. So I haven't defined what strongly contextual is. So this is non-contextual. This model is strongly contextual. Strongly contextual is what you may have intuition from this discussion, because our goal was to do this, right? At least greater than 0. But I can end up with such a scenario where even if it is explaining this, but there is some context for which it is giving 0, not greater than 0, then there is no way of explaining that empirical model by a non-contextual assignment. Even if there exists one context for which these hidden variables are 0, these probabilities, then this model has no way of explaining through a non-contextual hidden variable model. So that empirical model will be called strongly contextual. So then now you assign as much as you can in this lambda and as much as here, right? So okay, so this I will write contextual fraction of E, this 1 minus lambda now, okay? So the goal is what? You want to assign as much as you can explain some model with a non-contextual model. From there you get non-contextual fraction. And if you have non-contextual fraction, then you know that just 1 minus contextual fraction, right? Because it is a convex mixture. So calculating non-contextual fraction and contextual fraction will be similar. But I think the calculation, how to do the calculation, I cannot finish it today.
Yes.
So I have just introduced.
So
because that will take some time, I will have to introduce some matrices and all.
okay, maybe in the next meeting you can continue and take us to there. But just to try to understand, ask an intuitive question. But so basically the non-contextual, our motivation is to maximize non-contextual fraction with some technique, right? And then we can define the measure of contextuality. So it's quite something like that, geometrically speaking, that how far your probability point is from the non-contextual polytope. It's something like that, kind of.
Something like that, yes.
And another thing one can thought of, let's say you have this probability point and you do this optimization by the technique you will tell us in the next meeting, and you got some number, right? That's any NCFE will be some alpha amount you need. Now let's say there is a transformation procedure. From using that, I go from this probability distribution to another probability distribution, let's say, okay? And this probability, and that transformation, property of those transformation or the restriction of those transformation will depend on different scenario. If it is a single system, then the different transformation. If it is a Bell-like, CSSH-like scenario, it will be a LOSR kind of transformation. One can go from one point to another point, right?
Right.
Now, when you go to another point, maybe that point's NCF may be lower, or maybe higher, or maybe equal.
Yes.
So if that point's NCF is lower, then how can we be sure that this P is actual non-contextual? If it is higher, let's say, then how can we be sure that to reproduce this probability distribution, we need this alpha amount of non-contextual? Because with some local operation, we can go another point where the alpha value is more.
Yeah, I understood. So for that, you have to do a optimization problem. That is how to calculate this contextual fraction.
Yes, but in that optimization problem, has they taken over this optimization also? Have they incorporated this optimization also? That when you can transform the probability distribution from one point to another point.
Probability distribution means this EC, right?
EC, yes. You can transform the EC from one point to another point. For example, let's say you have Sirelson kind of EC. Then let's say for and the non-contextual fraction is, let's say, alpha for this particular, right? Now with some transformation, you can go from Sirelson point to another probability point. And to reproduce this, and there the non-contextual fraction, let's say, is greater than alpha. Okay.
But this model is already given to you, right? E is already given. I mean, I have provided you a data table that is already given.
But think of it in a CSSH context. With LOSR, if I can go to another probability distribution, that is allowed, right? You give me a row, you give me that E. With LOSR, I will go to another E dash where the NCF is higher.
Yes.
So then how can we defend that to reproduce
Yes,
E,
so-
I need
so-
this much?
So for that, we have to prove that contextual fraction by this kind of mapping does not increase under LOSR,
Exactly.
right? So
Maybe.
that is how we formulate the resource theory of contextuality.
Okay.
Exactly that. Yes. I mean,
All right.
actually, that result is there, that this contextual fraction, there will not be LOSR, because LOSR is the pre-operation for non-locality.
For non-locality case,
But
yes.
for contextuality, there are 3-4 different free operations, which are like translations of measurement by preserving context, then coarse training, and then taking tensor product of 2 empirical models, something like that. So those are some free operations. So under those free operations, it is proved that contextual fraction do not increase.
Okay, I understand.
So it is monotonic under those free operations. So that is the motivation of formulating this resource theory of this kind of contextuality.
And this is the starting
I think
point, understanding this
I think-
non-contextual.
So understanding
Sorodipta,
Yeah.
Sorodipta, you ask whether there is other
Yes.
questions or not. So anyone wants to ask any other questions?
Okay. Maybe if there is no other question, then
No, we cannot. I mean, okay, I have some questions, but
Yeah,
maybe those might not be very much related with these things. I mean, we can continue these discussions.
sure.
Yeah. So,
but you
so,
can
so
officially finish the recording me. And
yeah,
then,
I can finish the recording. Yes. So, yeah.